and to be honest, good answer. So the contents of today's talk episode pre-conventional farmers, so the paintings we're going to discuss it. Axis of the space, chart distribution, and recipe intention. Then there is a direct potential when the PN junction pass. So we'll see what is a direct potential. Well, after we'll apply the biasing conditions like power gas and reverse gas. But there, when we say about what is the diode equation, and the red potential distribution. Diodes like spot connections, eternal lamps, or any other laws which you know. So in generally, diode, not the diode, and PN junction is also called as a diode. So the term diode from the every groups meaning which means two and no device meaning is power. So the two power. So they use it in various electronic applications. Oh, madam. They use this diode to form transistor and film. So nowadays, whatever the IC chips, what we are using in electronic devices, in computers, and mobile phones, motherboard, different types of motherboards. So all are integrated circuits. In the integrated circuits, we used to see the different types of IC chips. So these IC chips will work on the operation of transistors. The number of transistors or lines of transistors are integrated on the IC which forms an IC and that are embedded into the one board and which is called as a SOC system also. So the present of the electron device which are running and which we are using now things it depends upon completely and transistors. So these transistors are used to define from the electronic device is called diode. So you see these same diodes are also used in the logical circuits. So we will see this is the one symbol of the diode P on. So P material and material are closer to place it to each other. This is the diode symbol and the P the anode is formed on the P-type material and the cathode is formed on P type. And this is a general diode what we use in the circuits. So this is the general description about the diode. So once I know PN junction is also called as a diode. The term diode from the tools is guide and also less which is nothing but it. And OD is a word which is nothing but a pass the two parts. It nothing but a diode. It is used in various electronic applications. We use this diode to form the transistor outlet. And these are the symbols of diodes. PN as well as that. This is the main symbol. Where the two terminals like anode and cathode. The P material indicates anode in the so let's see how the PN junction is formed. So we still have different types of material like conductor and insulator. But when coming to the conductor will conducts electricity, the good conductor of electricity such materials are called conductors and the insulator is the bad conductor of electricity. The type of materials are called insulator like glass, rubber. So these are the insulator examples. So here coming to the conductor, iron, copper, which comes under the conductor. So measurements until it's sold on, so they already have one more material that is called semiconductor. So the semiconductors are two types, the six semiconductors. So intrinsic semiconductor, we have two semiconductors, extrinsic semiconductor, we have two semiconductors. So the extrinsic semiconductors will get some impurities so that the charge carriers will increase their numbers. So when coming to that, we have the two types of semiconductor materials like P-type semiconductor and N-type semiconductor. So P-type semiconductor consists of million charge carriers and holes. We can see the P-type semiconductors are only excessive holes, which is nothing but the charge carriers are holes in the P-type material. So which is the acceptor atoms, which means the electrons will diffuse into the holes. And coming to the other semiconductor material used in this PN junction is called N-type semiconductor. The N-type semiconductor consists of excessive of the free electrons, which are the negative charge carriers and magnetic charge carriers, right? So in the P-type material, the magnetic charge carriers are electrons. So the P-type is acceptor atom, the N-type material is a donor atom. Okay, so when these two materials, semiconductor materials are placed to each other. Okay, so this general line the distance or the place when these two are attached, the exact middle point will be considered as a junction. So there's some type of operation will be occurred at the junction. Let's see how the junction works. What is the junction? What happens in the junction? With the two different types of that is acceptor semiconductor and donor semiconductor basically each other. Charge distributions. So diffusion current flows whenever P and N materials are joined together, and positive and negative ions are created when holes and free electrons are cross the junction and move to other side. This charge is called as a space charge. So in general, the P type material consists of majority carriers are number of excessive charge carriers and holes, and in N material the number of excessive charge carriers and electrons. So these two materials, two semiconductor materials, that is a positive and negative ion are placed together. That the general natural attraction, that is electrons will diffuse into the P type material. The majority charge carriers of N will diffuse into the P material. And this forms the uh, flow of charge carrier, that is a diffusion of charge carriers from one side to another side, which gives rise to a current flow. This gives rise to the current flow that we used to call that how the current is forming, right? By using these two types of semiconductors, P type and X type. So once again, I'm repeating the diffusion current flows whenever the current flows whenever P and N materials join together. That is because the positive and the negative ions are created when holes and free electrons cross the junctions and move to the other side. So this charge called is space charge. So this is the general P-N junction formation. So the white, whatever the white bubbles we see in the P regions are holes, and whatever the pink bubbles we see N region are the electrons. So which means the majority charge carriers, the number of excessive charge carriers in the N region are electrons, and the number of excessive charge carriers in P region are holes. And we have a little amount of magnetic charge carriers also, that are the electrons of P region, and the magnetic charge carriers are the N region. Okay, then the similar thing what we discussed in the last slide, that is how the current flows due to the positive and the negative ions from the created holes and free electrons cross the junction. So here also the negative charge ion from the N region and positive charge ion plus N region will diffuse from the junction from P region to N region and N region to P. So let's say one electron is diffused from N region to P region. So which means these electron will replace the one of the will replace to the hole, and this forms an electron, and this forms a hole. So that is nothing but the shifting of major charge is occurring, which is nothing but the charge carries a positive and negative ions are diffusing from one semiconductor material to another semiconductor. So this is the reason why we are getting the diffusion of current flows in these materials. So when at the first, before it is in biasing condition, that means if you are, when we are not applying any type of friction on those, when the two materials are combined, these two materials are combined, the N region then forms a junction. Junction is nothing but whenever at the junction, whatever the closest electronics, closest charge carriers on the P and the closest charge carriers on the N to the junction will diffuse from P to N and N to P. Okay, later on there forms a some immobile ions in the junction. So this comes in some place, some region. So this region is called as the depletion. So the depletion region consists of the positive ions and the negative ions. And these positive and negative ions are immobile ions, which means they won't diffuse into the P type, or they won't diffuse into the N. So this is, we use the diffusing capacity so that they will be called as a immobile ions. Okay. But these immobile ions consist of some potential, which we used called as a barrier potential, which is some kinetic energy of the barrier potential exists in this junction. So like this, when the P region and N regions are placed to each other, the diffusion takes place, and finally they'll form a junction, which we used to call as a depletion region. At the junction, they forms a depletion region. And the depletion region consists of some charge carriers, negative and positive charge network from P-type and N-type. And these are immobile ions. And in this region, there exists some potential is called as the barrier potential. So what is the barrier potential? So the barrier potential is also known as a junction potential or diffusion potential. It is denoted by VR. Okay, you can see on the diagram. Um, so this is a depletion region, which shows consuming the stress because of when the immobile ions are formed, and we have some negative charge carriers are the pin material and the positive charge person of the material. So this is the once when these two starting when these two materials are placed, the diffusion takes place and later on there forms a depletion region. This depletion region consists of the negative charge ions from P-type and positive charge ions and N-types, and these are the immobile charge ions. So charges of positive polarities establishes electric field, also known as the barrier potential. As we can see, this depletion region we consist consists of positive and negative ions. So these positive and negative ions establishes some electric field to break this electric to stay in the depletion region. The forms electric field, but electric field is nothing but it is to cause a barrier potential. And on the depletion region, whatever the barrier potential is, so the barrier potential is also called as a junction potential, diffusion potential. Okay, so what is water barrier potential? Okay. So when initially when these two are joined, that is the p-type and n-type that is initially joined electrons from the n-type migrate into the p-type material. Less electricity, more electrical density will be there. When electrons spins a hole, both electrons have disappear as a gap, and this is bond is filled out. So this is known as the if you charge progress, the depletion law, the layer acts on the insulin. Layer as it consists of some electric field in this depletion layer. This depletion layer can go further diffusion of the charge carriers from M to P and P to P. So this will act like a type of wall between these two materials like the junction. So due to this, the further flow of charge carriers it won't take place in this PM, P and N in between P to P and N. Okay. So this is what we can see initially when these two P and N are placed at one place. Next, so whatever the electric field which exists in a negative or positive charge carriers over the uh, depletion region. So this silicon, if you are using the silicon material, the two p-type semiconductor levels like that, and then the potential value of this walk is up to 0.7. For the generated material, the potential value is up to 0.3. So we, for these depletion region where reaction happening as a insulator, so to overcome that insulator or because from current conductivity in this for this intensity found material, you need to apply the operation to break the barrier potential of simply 0.7 inch, more than 0.7 inch. Using break the insulator with the diffusion rate, potential order existing the diffusion rate. So the applied voltage equal to 0.3 inch. So only there will be a flow of charge per the stage tester, and there will be a power. These two values must be remembered that is for the same. It's the potential barrier voltage drop 0.7 volts or this equivalent potential barrier voltage drop 0.3 volts. And this is the PN junction. PN junction material. That is, you can see the depletion of the region, which is a ash color before forming the depletion region. There exists a one junction, which is a yellow line. And after the forming the depletion region, this ash region will hit the depletion region, which contains the end of the ions. And this one of the ions establishes the electric field. Electric field is nothing but a potential gas. And so the genuine and the potential value is 0.7 7 volts, sorry, 0.3 volts, and for the uh, silicon material, the potential barrier is 0.7 volts. Right? And the P, we used to have the two terminals for the diode, that is anode and cathode. And the P material side used to have a terminal called anode, and for the terminal on the N side used to call as a cathode. So the general symbol of a diode, which is very important to remember to the diode side. So which is cathode and which is anode. So diode power using the PN junction. Okay, in generally till now we seen what is how the junction is formed, what is depletion region, what is the potential barrier existing of depletion, how the depletion region is formed. Okay, and why the depletion is acting as a uh, insulator in between P and N material, and which is not going to go to charge barriers. So this is what in the initial stage when we went applied many type of the biasing condition like any type of the external fuels. So now to break uh, the insulator property at the depletion region so that again there should be a flow of charge gaps should exist in between P and M material. So there will be a current which can be used in a different type of electronic devices. So this valve should shrink to the region or the width of the depletion region. So further will be used to see the two different biasing conditions. Like first one is the forward bias condition, second one will be the reverse bias condition. So what is forward bias condition? How the external, what type of external force they are going to apply, what is their connections, what is the P-type material, which terminal used to connect component, which material used to connect. So you can see in the diagram. So we have a P-type material and N-type material and depletion region. In the depletion region, whatever the electric field is there, the electric field is nothing but potential barrier. The potential barrier direction is from N to P, which exists in between directions from N to P. So there should be some opposite force to overcome this potential barrier so that the depletion region decreases, which is acting as a wall between the P and N material, which is not allowing to flow the charge carriers. So that's why we are calling it as an insulator plant. So to overcome this, we need to apply some opposite force to shrink the potential barrier voltage in the depletion reaches. So for that purpose, we need to apply some opposite force, which is from a battery. We can see that positive terminal and the negative terminal. Positive terminal is connected to P-type material and the negative terminal is connected to N-type. This is very important consideration. We need to see the forward bias condition. The positive terminal from a battery should be connected to P, and a negative terminal should be connected to N. Okay. The positive terminal is connected to P, and the negative terminal is connected to N. So then these opposite, when the positive terminal is connected to the P, the positive voltage from the battery is applied to the P material, and this is will be act as an opposing field to due to the battery. So this is what the electric field or the potential barrier which will exist in the depletion region. For on that field, we are applying some opposite field. Okay. So due to this, up to 0.7 volts, whatever the voltage you are applying up to 0.7 volts, there will be no shrink or the no decrease in the width of the depletion region. When the battery opposing force is opposing field is greater than 0.7, then the depletion region will be the width of the depletion region will decrease. And once the depletion region decreases, so the depletion region width decreases, here starts the flow of the charge carriers from P to N and N to P, and there we can say the current flow between the material. So the depletion region shrinks and the current begins to flow. And when we apply forward bias junction, you can see. Forward bias is a condition that allows current to free and junction. A DC voltage that is V bias is applied to the bias as well, which is called the back bias, which is called as well. That is, this is what connection. But we are indicating with a V bias. It is applied to it. Diagonal bias and bias. Positive side is connected to P region. The detection, the positive terminal is connected to P region. and the negative side is connected to the negative. Then you can see, look, I mean, this negative terminal is connected to the negative. V bias must be greater than the barrier potential. So this V bias is acting as a opposition field to the depletion region. So the depletion region equals the barrier potential. Suppose if there is a silicon material has semiconductor of period P material and the barrier potential is 0.7. Okay, to get the current to PN junction. So we must apply the V bias must be greater than barrier. So that is 0.7 for silicon and 0.3 for genuine. Then once we apply the greater than 0.7 volts for the silicon material, so which is a stronger opposing field than the barrier potential. So this barrier stronger opposing field will shrink the drift, that is a bit of the depletion region, and the heat of the depletion region will decrease, and there starts the current flow. Current flow will begin in the PN junction. So what else you can see this. In earlier case, we used to have this much of the depletion region, and when we apply the opposing force, that is the opposing force of P terminal, positive terminal is connected to the P, and the negative terminal is connected to the negative. And then, due to this opposing field, the depletion region will decreases. The depletion region will once it decreases, then there is the start of the flow of the charge scale. As you can see, the electrons are moving to the jump region, and holes are moving into the heat because the electrons will attract to the positive terminal and holes will attract to the negative terminal. So this requirements can build the flow of charge carriers is this P and N material as the depletion region decreases due to the forward bias conversion. Okay. So this is what the forward bias conversion is. Okay. Yes, also very much for forward bias there. For condition that allows the current distribution and DC voltage is applicable. They have attached to DC voltage is of positive voltage and the positive is connected to the region, which is anode, and the negative side is connected to the region, it is cathode. The bias must be greater than barrier potential, and the barrier is 0.7 and 0.3 matter. Opposite forces are applying to the battery, that is P bar should be greater than the barrier potential, then only the depletion region of the depletion region will decrease. The depletion region will decrease. Once the depletion region will decrease, then it is the charge carrier. So now come to the reverse bias. So reverse bias condition in the reverse bias will reverse the terminals. That is the negative terminal is connected to the positive P type, and N type is connected to the so the positive terminal is connected to the. So in this case, we are not we are not supposed to apply the opposing field from the battery, but we are supposed to apply the supporting field to the battery, supporting the field to the. So as the positive voltage is applied to the can material, so this gives the supporting voltage to depletion region. So due to this, the depletion region will expand and opposes the flow of current. Opposes the flow of current. Okay. You can say the reverse bias is condition that reverse the current. So that gets in forward bias, that's the flow of current. And when we apply the reverse bias condition, which is a supporting voltage is applied to the barrier potential and the depletion is there. So due to the positive side of the device is connected to an end, whereas the negative side is connected to the and the depletion will then get wider with this configuration. You can see the depletion region will increase in this case because the applied voltage in this case, that is in the reverse bias condition, is supporting field, supporting voltage. You can see in this diagram. Negative terminal is connected to P region and the positive terminal is connected to N region. Due to this, this is the what about supporting electric field, supporting voltage applied to the depletion region. So depletion region which is increased in this case, and the more immobile ions will be considered in the depletion region. As the electric field extension layer increases. Even though there is an increase in the total depletion region, the minority charge carriers which are present in the P region, that are the electrons. Obviously, these electrons will attract towards the negative current and the holes which are attracted towards the positive one. So between this, there exists some type of a reverse bias condition as well as junction. So these are the diode characteristics you can see. When in the power bias, so when you apply the voltage, that is the battery voltage starts from zero. When you apply the zero, there is no current, there is no flow of charge carriers. If you goes on applying like up to 0.7, you can see there is no current is exit, no current flow because the direct potential is up to 0%. So the whatever the opposite field, opposite voltage we are applying that for this, that should be greater than barrier potential. So once the voltage is applied voltage V versus greater than barrier voltage, barrier potential, we can see there is a rise of the current. The current will increase as increase the voltage. So you can see the maximum current is 60. Coming to the reverse bias condition, even though the depletion region increases, you can see that the some amount of voltage on is supposed to see the reverse current. That is the this reverse current is due to the minority charge carriers. It is the minority charge carriers. So once the minority charge carrier, the existing current is called reverse oscillation current. As it goes on, giving the supporting voltage for the depletion region at one place, what is exact example of minus 50 volts. There occurs some which is called as a breakdown voltage. So there is a sudden increase in the current decrease in the current. You can see that is a breakdown voltage. When the breakdown voltage is comes, there will increase in the current. So these due to this, there will exist our avalanche breakdown, and further if you increase more voltage other than the breakdown voltage, there is a chance of getting a error that will get damaged. The points to remember in the is diode cannot conduct in the reverse bias condition, and diode can conduct in forward bias condition. Silicon diode has a voltage of 0.7 volts and germanium has 0.3 volts. And this is the diode model. So you can see the ideal diode model. So when you apply some positive voltage that is in forward bias condition, so diode will be sorted so that whatever the voltage we applied that will lead to the load resistance. That is a forward bias condition. And for the reverse bias condition, you can see the negative terminal is connected to the anode and the positive terminal is connected to the positive. So when you apply this reverse bias condition, this will react as open circuit so that the ideal current will be getting the zero. So you can see the V characteristics of ideal load. Like when you apply the condition, when you apply the voltage, you're getting the maximum current. And when you apply the voltage, you're getting the zero current in reverse. Because the reverse bias condition, the ideal diode will act as open circuit, and in the forward bias condition, the ideal diode will act as a short. So the barrier potential and the forward dynamic resistance and the reverse current are all neglected. In diode models, you can see similar condition, again, forward bias condition, then go to the 0.7 and the practical ideal diode we are getting same current. And for the reverse bias condition, barrier protection and forward dynamic systems and the reverse current are all neglected so that the current what you are getting is zero aspect. Let's see some of the diode applications. So the diode, when it is in forward bias condition, this diode conducts the current and this diode can be the rectifier. So rectifier is nothing but this converts from AC to DC. AC current to DC current. So here you can see in the half-wave rectifier, which is easy to convert from AC to pulsating DC. A full-wave rectifier, material rectifier, and we used to use the two diodes. Actually, we will use the two diodes. In the bridge rectifier, we use the four diodes. You can see the positive and negative ions, sorry, the positive cycle and the negative cycle will be neglected and it will be converted is shifted to positive also. So diode can be also included as a capacitor. To the positive cycle, and on the positive cycle you have which indicates the charge of the capacitor, and the negative cycle, what where the negative cycle is, will indicate the discharge. So the capacitor properties is charging and discharging that can be seen in this, which is considered as a ribbon. So this will charges and discharges, and whatever the ripples which are present in the output of this full rectifier will be neglected, and finally we used to get a DC voltage. Thank you.